Okay, let's spend some time talking about Chapter 5 in our textbook, Thin Film Transistor Flat Panel Imaging, which is the majority of what y'all are working with out in the clinical sites. Like I mentioned, she does some assumptions that we've read the chapter on computed radiography, or what she calls PSP, plate design photostimulable phosphor plate radiography. So we're going to be using some terms from that, but we're also going to be exploring technology, as well as we'll talk a little bit more about pixels and where pixels come from, and a good example of how to think about them. So our objectives, first off, is just to define what a TFT, flat panel digital image detector is. We'll talk about construction of either direct or indirect capture, and we'll differentiate between direct and indirect capture, but I'll give you a really simple way to differentiate between these systems right off the bat. She doesn't really point this out, but she kind of alludes to it in the first paragraph in the textbook, that one of them is going to use amorphous silicon, the other one's going to use amorphous selenium. Right? So an easy way to remember which uses which is indirect starts with an I, and silicon has an I in it. So indirect is going to use amorphous silicon. Right? Direct panel is going to use amorphous selenium, and we'll talk about why that's the case, but that's just an easy way to remember it. We'll talk about gadolinium oxysulfide style detectors, and then we'll talk about the thallium-doped cesium iodide detectors. We'll talk about designs for these and how it's related to performance measurements like modulation transfer function, detective quantum efficiency, and then we'll talk about specific artifacts of this kind of system, because computers are great when they work, but when they don't work, they're a nightmare. And so a big part of what you're asked to do as a technologist is to be that person to understand why the system isn't working, or just to even notice that it's not working in order to contact the people who can fix it. So these amorphous silicon, amorphous selenium detectors were first introduced in the 1990s. These were the first devices to move beyond cassette into a detector that was like embedded to reside in a table or on a wall stand. So some facilities that you're working at are using flat panel detector arrays that are kind of that first generation, where they're built into the table, they're built into the bucky, right? Also, some of what we're seeing now is more and more Wi-Fi enabled or even Bluetooth enabled detectors that can be used, again, similar to a cassette, right? So there's powers in both of those. What we're going to focus on, rather than all the different types and styles that are out there, we're just going to break them down into direct or indirect. But the important thing for you to understand is that inside of this detector, there's things that are capable of detecting the X-ray, and they need to be protected themselves. They're very, very fragile systems. So one of the things I'm seeing more and more on Facebook is people posting pictures of an image, and they're saying, I think the detector got dropped, right? I think that the indirect detector got dropped. Is this an artifact related to it being dropped, right? So part of the reason why we need to know in some detail how these systems work is then to see, is this evidence of the detector being damaged, or is there something else going on? Because they are very sensitive systems. And you'd want them to be sensitive systems because they're trying to detect something that's very difficult to detect, right? To do that, they're going to use an active matrix, right? So this is going to consist of a bunch of technical jargon, right? But what she calls it is a flat panel array with X-ray absorption material. This is illustrated in our textbook on page 66. And so it shows us the X-ray absorptive material and the detection matrix that's beneath that or underneath that absorption material. And then it has a bunch of integrated circuits that are then used to read out that matrix. So the two big things that we're talking about inside this is that there is going to be a computer part, and then there's an absorption part, right? A computer part and an absorption part. They have different rules that they follow and different expectations out of them. For the most part, if we dropped the detector and we suspect that some part of it is damaged, it is probably the absorption part, right? The computer part, if it's damaged, you're just going to get system error messages. But if the absorption part is damaged, you're going to get weird picture artifacts, right? So I like this illustration here. And then in this next illustration on the page right here, she's zoomed in beneath the absorption layer into the active matrix layer, and she's showing us these thin film transistors, right? So we're going to spend some time on just this illustration right here. I know it seems like a very simple illustration. There's a lot going on in this illustration, so I want us to kind of draw on it some and to think about it, or at least draw a picture of it. So that's going to be part of our learning today. So I will be coming back to that. But before we get down to the nitty-gritty with that, let's just kind of get a good survey of the lay of the land and what are the problems that we might encounter. So for the absorption materials, we're going to use either photoconductors or photoscintillators, right? An example of a photoconductor is amorphous selenium. Amorphous selenium has the ability that if an X-ray interacts with it, it produces electricity. That's what photoconduction means. X-rays are essentially a form of invisible light. So in the presence of light or in the presence of something, they emit what? Electricity. That's what conduction means. So that amorphous selenium is that photoconductor, right? Amorphous silicon, I said we're going to use in an indirect system. So file it away for just a second because it is not a scintillator, right? Amorphous silicon does not scintillate. What scintillates are things that interact with light or interact with X-rays, and they produce visible light in response. So gadolinium oxysulfide, europium-doped cesium iodide, those in the presence of X-rays emit light. So we're going to call those scintillators. Those are scintillating crystals, scintillating phosphors, whatever you want to call them. It means by stimulation they emit light. Yeah, bless you. So the active matrix flat panel image detector, right? This active, I would probably just call it the active matrix or the flat panel. It is capable of responding to these different absorption properties, right? So if you have a direct system, the thin film transistors respond to photoconduction, right? They respond to photoconduction. If you have an indirect system, they respond to light from the scintillator. So how the system responds is important, but at its foundation level, the house is essentially the same, right? So we have two houses, right? One house is full of light, right? Like a greenhouse, right? It's full of light. That's that indirect system. We have another house that is just full of electricity. It's an electrical house, right? But the foundation work is exactly the same. That foundation, that active matrix is essentially the same, okay? So what is it? It is a 2D pixel array, right, fastened to a thin glass backing or substrate. So oftentimes that substrate, when you see substrate and you're talking about computers, you can think silicon, but I don't want to confuse you, right? Because one of these, both what I just said is both these systems use silicon at some level, right, for the substrate of the thin film transistors. That's how integrated circuits work, right? So I can show you demonstrations of like a breadboard or what that is. So the foundation is silicon, and we're gonna, or glass, and we're gonna build up integrated circuits on that foundation. So the foundation's the same, right? But I don't want that to confuse you, so it may be helpful just to think about it as a substrate. So we then attach that absorption material to the thin film transistors. We just lay it over them, and we know that they're going to be capable, this array of pixels is going to be capable of transmitting the signal that we receive from the remnant beam exiting the patient and turn that into a picture, right? So the book talks about this is an efficient device that measures X-ray absorption rather than counting or measuring the actual X-rays. So the thin film transistors are blind to X-rays, completely blind to X-rays. You can X-ray a computer all day long and it will not detect a thing, right? This is one of the reasons we want to weaponize X-rays from the very beginning, is because they do not damage electrical systems. So what do they do with bombs to make sure the bombs are built right? They X-ray them. They get gigantic linear accelerators and they do CT scans on missiles, right? Because it can't damage it. It's not going to cause a spark. It's not going to do anything, right? So the TFT, why do you care? The TFT, it's blind to X-rays. It needs the absorption material to tell it something's going on out here, and then it can pick that up and turn it into an electrical signal. So, like I've alluded to, there are two major types of these. There is the greenhouse full of light, and there's the electrical house full of electricity, right? Indirect being the lighthouse, and direct being the electrical house, right? And this X-ray absorption material determines whether it's a direct or indirect system. It's not the thin film transistor. It's not that substrate. You could apply that substrate to either one of these systems. The foundation's the same. Just depends what kind of house that we build on top of the foundation. So the most simple of the two, we've already said, is the direct conversion. It's simple, it's elegant, it has a high detective quantum efficiency because it's not transmitting things into light. It's just the X-rays interact with a coating material, that amorphous selenium. It's a photoconductor. It turns the X-rays into what? Into electrons, right? And that's what's registered by the thin film transistors. That is simple as it can be said, right? In fact, I don't even know if our textbook illustrates it. It's that simple, right? There is an illustration of it, and I will share it with you in a minute as part of an activity, just so you're not completely in the woods on how to illustrate this. But just imagine X-ray striking the absorption material. The absorption material emits electrons in response, and the thin film transistor grabs those electrons and starts to store them. Generally, the thickness of that amorphous selenium is part of how we'll control for the system. For general X-ray, we will use a thicker amorphous selenium absorption level than for something like mammography. This is interesting because this is similar in some ways to the way film worked. With mammography, we used a less sensitive film system, right? Than we do for general X-ray. Why would we do that? Well, we want to be aware that not all the X-rays we're trying to pick up are good X-rays, right? So if we use a thinner detection system, we are less likely to capture some of those X-rays that are no good, right? But what happens as a result of that to patient dose is patient dose goes up. So for general X-ray, we do not need a high level of sensitivity, so we slather that amorphous selenium on there real thick, 50 micrometers, 50 microns. But it's going to be more responsive to X-rays, so we decrease patient dose. So that's why those thickness differences are there. One system is designed to pick up more fine detail, and it is that one that has thinner absorption material to it. And this material converts the X-rays to electrons, which are then stored in the thin film transistor as part of the active array. So this thin film transistor system is, it calls it photosensitive. It's probably best just to say it's sensitive to whatever signal it's receiving, in this case, electrons, right? And each one of these elements right here, each one of these elements we'll refer to as a del, right? It just stands for detector element. So if a pixel is a picture element, this is what makes pixels. It's the detector element. This is where the pixels come from, right? So you notice immediately she starts using those terms interchangeably, right? I mean, probably the more accurate way to express this on this slide is each del contains a photodiode that absorbs the electrons and generates electrical signals. Each detector element contains a photodiode that absorbs the electrons and generates the electrical charges. So I'm probably going to change the slide to reflect that. We want to be careful about using the terms interchangeably because DELs actually do things. They're physical objects that do stuff, right? They capture things. They capture electrons. They transmit those electrons. Those are actual activities that a computer can do. A pixel is just kind of an idealized thing that just exists out there in mathematical land. So here's an illustration of that. So she talks about how there is a field effect transistor, an FET or silicon TFT, that isolates each picture element. Basically, there's just two different terms. They are doing essentially the same thing. They're isolating individual pixels. So the DELs are capable of, what I'm saying here is the DELs are capable of receiving information from more than one pixel, right? The detector elements are larger than a pixel, is what I just said. So it isolates those charges and determines what part of the pixel should be associated with. And then more than 1 million pixels, and that's important because if I had to make a detector array that was made out of 1 million parts, that would be a very, very sensitive system, right? And by sensitive, I mean easy to break, easy for it to malfunction, all sorts of things. Electricity would be interfering with every part of the process. So we made these things larger and allowed them to sort through for different pixel sizes. So we'll look at that again. So we have a line of TFT switches, and they're each associated with a storage capacitor. What is a capacitor? It's just something that can store electricity, right? So where are we at in the process? We've x-rayed the patients. The x-rays have passed through the patient. They've struck the image detector, right? And we're using a direct system. Those x-rays directly turned into electrons, and those electrons just got stored, right, in a capacitor. That's how we're going to read this thing out. We're going to discharge those capacitors. Now, if you're wondering what in the world is a capacitor, just think, bro, don't tase me. That's what a capacitor is. It's a taser, right? A taser is a very large capacitor. It's the reason why if you're ever in a junkyard as a kid like I was, you shouldn't open up old television sets. Not only are they full of lead and crap, they have gigantic capacitors inside of them that would knock you across the junkyard, right? What are we going to use those capacitors for in direct capture? They're going to capture our image, and then we're going to discharge them as a way to read that image out. So just think about getting tased, and that's what we're doing. We're discharging those capacitors to release that electricity, and there's a lot of information in that. Just ask anyone who's been tased how much information's in there. All right. So we need a way to control that, as you can imagine. We don't need to just be discharging capacitors left and right. That would not be helpful to anyone, right? So we're going to use integrated circuits to control that. Integrated circuits, what are those? They're just computer parts. They're highly, finely tuned computer parts. And so they consist of essentially ones and zeros, and they determine, should you discharge this capacitor, yes or no, on or off. So we just go through the switches and we determine where the capacitor is discharged. She gets into the weeds with that right here on page 69. I think you can ignore all of this. If you understand this slide, ignore this junk. Don't get into the weeds here, right? Just understand that we had x-rays, they passed through the patient, they interacted with amorphous selenium since it's a direct system. They created electrons, we stored those electrons, and then the computer read out the storage capacitors. And you're good. This, of course, is done very fast. So that's all that I'm going to say about direct systems, right? The indirect systems, interestingly enough, we're going to spend more time talking about indirect conversion, right? Because it's a more complicated system, but it's probably not where the future is going. Right? The future is probably heading more towards direct land, right? But we need to be familiar with this process. It's a two-step process, right? This is the lighthouse, or the greenhouse. We're going to turn the X-rays into light. We're going to capture that light in the thin film transistor array. So the foundation is the same. That thin film transistor is the same. That active array is the same, but what we're capturing in the active array is different. So that two-step process is significant because, like Ms. Thorne indicated, we are going to lose some information just in the process of turning the X-rays into light. That's why we're going to spend so much time talking about this, what we lose. So we will use a phosphor, a scintillating phosphor. What does that mean? In response to X-rays, it emits light. That's what a scintillating phosphor does. And this goofy chemical here is gadolinium oxysulfide. Gadolinium oxysulfide. Or we'll use thallium-doped cesium iodide, right, to absorb X-rays and produce light. One of them's better than the other, but one of them's also more fragile than the other. And that's what we're saying when we say it can be either structured or unstructured. The gadolinium oxysulfide is unstructured. This is illustrated on page 67 in our textbook, right? So it is what was sometimes called a turbid phosphor. Gadolinium oxysulfide is turbid, right? It is unstructured, it is turbid. Those terms are interchangeable. What does that mean? Well, the illustration, I love this illustration here. It actually has a picture of what the little molecules look like. That's a gadolinium oxysulfide molecule. It just looks like packing material, right? When an X-ray hits one of these little pieces of packing material, they emit light in all directions, right? So that light is unstructured because the crystal is unstructured. And so this results in light going out in all directions. That is a confusing signal. If you got light going out in all directions, those light photons are bouncing off of things, it's making a muddled signal. That's what turbid means. When I think about the word turbid, I think about a mud puddle. It's kind of like a mud puddle, right? If you stir up the mud puddle, what happens? Mud everywhere, you can't see anything, right? So that's what gadolinium oxysulfide is. When would you need a mud puddle, right? Well, a good example would be something like combat. If I'm in a combat situation, I want a gadolinium oxysulfide detector. The military loves gadolinium oxysulfide detectors. Why? Because these things are getting dropped all the time and people are getting blown up and stuff, right? We need something that is not going to be very fragile. So it's turbid, that's the drawback. What's its positive? It's turbid, right? It's not going to get broken. Like, you can stir the mud puddle up and what happens? The mud settles back down. You're not going to break it, right? You're not going to break it. So these are more resilient machines, like archaeologists that go to, X-ray mummies and they're dropping detectors and stuff like that. They want a gadolinium oxysulfide detector. Okay, well, we've already indicated what the drawback is. Let's talk about cesium iodide real quick. This is a really beautiful illustration of cesium iodide, right? It's not turbid, it's structured, right? Cesium iodide crystals, they actually look like crystals to me. They've got like these little tunnels to them, right? It's quite beautiful if you look at the illustration on page 68. So when X-rays strike them, the tendency is that the light will be either going down the tube or up the tube. It's not turbid, it's structured. What's the drawback with that? It's fragile. It is a very fragile thing. This is the one you would worry about dropping. Let's talk a little bit more about that actual process. Here's a cutaway image, almost like a little slice. I think it's on the top of page 67. It shows the X-ray photons exiting the patient, the remnant beams exiting the patient, striking, in this case, a cesium iodide scintillation layer, right? So we have a sensitive one. We have a structured layer here. This cesium iodide is going to absorb the X-rays and emit light, right, in a structured way. That light is then incident on the TFT array. So each little del in the TFT array now is receiving that light signal, right? And it converts that to an electrical charge, right? This is why we need, so you might be wondering, well, you said earlier the TFT array was completely blind, right? So there is one thing that's missing here in this illustration, and it is the amorphous silicon, right? Our textbook did not do a very good job of pointing that out. We need something over the TFT array that basically turns the light into electrons, right? Turns the light into electrons. That's going to be the amorphous silicon. Amorphous silicon is capable of turning the lights into electrons, which are then received by the TFT array. So that's the two-step process. Cesium iodide in this case, light incident on amorphous silicon, that's what's received by, the electrons are then what's received by the TFT array. So this light is converted into an electrical charge by a photodetector. She says hydrogenated amorphous silicon. If you just remember amorphous silicon, you're fine. So here's a side-by-side comparison of gadolinium oxysulfide on our left with its turbidity, its unstructured nature, and cesium iodide, thallium-doped cesium iodide crystals on the right with their very, very fragile but very, very structured nature. So she talks about how the gadolinium oxysulfide are often like little powdered granules in some kind of polyurethane material. And the light's going to be generated in all directions. It can be used in a rugged or combat type situations. Versus the cesium iodide, again, that very, very fine crystal shape. These are 5 microns wide, which is a size I can't even imagine. Like I feel like when you're talking about 500 microns, I can kind of picture that, how that's related to like a millimeter or whatever. But when you get down to 5 microns, that is incredibly tiny. Needing it, this image is clearly taken with a microscope. And so imagine something that's very, very fragile and very, very small. That's what you have in your hand when you've got one of these detectors. So please be careful with it. This cesium iodide detector, like we've talked about, is going to have a higher DQE, right? It's a higher detective quantum efficiency. Why? Because it is emitting the light directly toward the amorphous selenium in the TFT array. In the past, these cesium iodide detectors could not be practically used in portable type detectors. Why? Because they were that fragile, right? They were that brittle. So it is not designed to exist outside of a very highly protective environment, right? We are making advances in this material that would allow us to use it, right? So my guess is in the future what we're actually going to see is kind of a back and forth, a bit of a war between the indirect capture and the direct capture. They both have advantages, right? We're going to see a bit of a war between gadolinium oxysulfide and cesium iodide with indirect capture because, again, both of them have helpful uses. Unfortunately, some of that war is going to be mitigated or negotiated by people who are politicians who just hear, oh, it's got a higher DQE, it must be better, right? So there's going to be always that tendency to simplify this stuff. For what do you need to know as an X-ray tech? It is helpful to know what you've got in your hand, right? What kind of detector are you playing with? Because it does affect how you work with it. It does affect, if you're in management, how you would expect your techs to work with different things, right? What is the level of expectation around training for these things? With gadolinium oxysulfide, you can throw that one at a student and let them go to town. It's fine, right? With the cesium iodide detector, you might need to have some kind of in-service to tell techs, okay, this is the way we're going to use this detector in this department. All right, let's talk a little bit about performance characteristics of these different systems. Some of the slides a little bit cut off. So we do not need to get into the weeds of all the complexities of how the system works, but we need to know enough about it to know when it's not working right, right? So again, we probably kind of a little bit of a typo on the slide. Each DEL contains a sensing component and a switching component. Each DEL contains a sensing component and a switching component. That's illustrated here on page 66. We have a charge collector portion and a TFT switch, right? A charge collector and a TFT switch. If you need an illustration of it, it looks a little bit like the great state of Utah. Do y'all know what Utah looks like on a map? I'll draw a picture of Utah. So that sensing component depends on the type of absorbing material and the vendor's choice of construction. So again, anytime you see vendor's choice, just think, don't need to know that. But what we do need to know is that we've got this amorphous selenium is a sensing element. So for the direct capture systems, we have a sensing element that's built into the TFT. We'll sometimes call this a storage capacitor. All right, for the way that these things work, we just need to know that there are a lot of little tiny wires inside these things. And those little tiny wires are going to be part of our problem. Now, oftentimes they're just integrated circuits, so it may be wrong to think about them as wires, but they're these highly complicated integrated circuits, right? But what you need to know is the way it's read out, they're going to have a row of DELs connected in the same horizontal control line, and then a vertical data line, right? This is illustrated, this is what she's getting at here on this illustration, right? All that I would think about this as being like is it's like a bucket brigade, right? So imagine that this room was full of water, right? We stored all this water in this room, right? One of the most efficient ways that we could drain the water out of this room would be to partition the room in rows and then just have a bucket brigade that empties out each row, right? That would be one of the most efficient ways we could drain this room. That's what this thing's doing. It's throwing the bucket brigade at all that electricity. So I do not necessarily expect you to understand how it goes through this process of reading things out line by line. If you understand that it's read out line by line, you're good. It continues from, once it's finished with row 1, it goes to row 2, row 3, row 4, etc. That's all that this illustration is showing us, how those DELs are read out line by line. So all of the kind of stuff that looks like this, I'm saying you don't need to know, right? So here's an example of stuff you don't need to know about this. What you do need to know is how that affects performance of the system, right? The fact that it's read out line by line and that we've got tons and tons of electrical bias that's being processed by this, we need to know as X-ray techs, right? There's two things that can result from this, right? Two things that we should understand. First, spatial resolution and detective quantum efficiency, right? I guess that's really two things, but numerical measurements of spatial resolution and detective quantum efficiency are going to be influenced by this. And the other thing is going to be low contrast stuff. Low contrast stuff. So she's saying there's a direct connection between modulation transfer function and detective quantum efficiency. And then the separate thing would be low contrast stuff. For the most part, the TFT flat panel systems, the direct capture systems, are going to have the higher DQE. Okay, let's talk about the artifacts that can result when our little bucket brigade isn't working right. If we took one bucket out of the bucket brigade, all of a sudden there would be a section of water that wouldn't be drained. We're calling that a dead pixel, right? A dead pixel. So we'll look specifically at that. We'll also look at gain calibration, and then we'll also talk about structural damages. So things like dust, scratches, stuff being dropped, things like that. So some pixels may be malfunctioning or dead, not functioning at all, right? Some detector elements, in other words, some portions of those detector elements may be not working very well, right? So some part of the state of Utah may not be collecting taxes very well, right? The chances are other towns in that part of Utah are still collecting taxes. So some parts of the Dell may not be working very well, right? We would call that a dead pixel, right? As the detector gets older, the number of dead pixels will increase, right? These might not be detectable if they're located at the edges because we're primarily focused on is the center of the X-ray image. And also manufacturers build in software protocols to detect and identify and isolate dead pixels. You've probably all seen or had a cell phone that all of a sudden you've got this one little red pixel on the screen, or a computer laptop that's just got this one funky part on it, right? That's what we're talking about. We would not want that on an X-ray image. This next one, so I feel like that's a pretty obvious one to think about. This next one's a little bit more difficult. Incorrect gain calibration, right? So imagine that as we're emptying the water out of this room, some people are better at emptying water than others, right? Let's say that. And if there's some people who aren't pulling their weight, we would expect their section to have some artifacts in it, right? That's what's happening when we have incorrect gain calibration. As the image receptor is being read out, are there portions of it that aren't being read as well, right? Are there portions that aren't being read as well? So this would be a flaw in the detector. And if an area has a large amount of dead pixels, or if there's an area of the detector that has poor connectivity, it's not being read as well. And this creates a noticeable artifact. Oftentimes what we do to correct for this is called gain calibration or flat fielding, right? You may remember I've talked about this once before when we talked about photosensitive phosphor plate stuff, that we had to do flat fielding or gain calibration. And this is one of those makeup metaphors, right? So the idea with this is this would be like applying a makeup foundation, right? There's a blemish somewhere, we're going to apply lots of foundation to that area, right? That's that gain calibration or flat fielding. We just want a flat field to work with. I'm thinking about a meme that Miss Castle included on some of her stuff earlier is a picture of Freddy Krueger. Let me show it to you all really quick. It's pretty good. So the way that we would correct for it is basically to do the Instagram effect to the detector, right? It will mask those defects, right? And hopefully it will not obscure information that we actually need. Our textbook shows us this illustration here. I don't know if you can see it on the screen, but there are some very faint, and this is interesting, Utah-shaped things here, right? I'm not exactly sure what they are, but they are definitely resulting from a incorrect gain calibration, right? So we need to do something on the software side, probably with this one, to get rid of that artifact. It's a very faint artifact. It may be more apparent on your computer screen. So these faint images here, right, can affect circumstances in clinic, and so we have to look at what's the manufacturer's requirements for calibration of the system. So sometimes this requires engineer to come in. Sometimes it's just part of the actual setup and daily calibration checks. So again, if you're asking, how would I fix this, right? The question might be, is the early morning tech doing the system's, the manufacturer's required engineering setup? Are they doing the gain calibration setup correctly? And that actually is a big question, because oftentimes human error is what can introduce these faint problems. That's the example. The next example she offers is looking at a different problem, but it is a human error example. So image lag or incorrect offset correction. So some systems, in fact almost all these systems, have the ability to take images faster than the detector can accommodate. So it is helpful to move at the speed of the system. If an image is taken before the detector releases all the previous signal, before all of the water is emptied out of the room from the previous picture, you're going to have water from two different exposures, right? So if we haven't completely discharged everything that's in that storage capacitor, it will have almost like a double exposure going on, right? So here's an example of just that. And if I remember correctly, it might be the next one that we'll be looking at with this one. So in this case, the detector was unable to eliminate all the signals from the previous image, right? And so this is a case of a patient who was probably 2-view chest x-ray, but the right marker from the PA is still on the lateral image. The faint image of that right marker is still on the lateral. The tech was moving just a little bit too quickly for the system. Maybe it was a slow day on the system, or maybe the computer was going through some kind of reboot or calibration and we got this error. So, if you're seeing this type of thing in your system, you may just need to work a little bit slower, right? Delay some of the time between exposures, make sure that you collimate appropriately, set appropriate technical factors. If you're doing a procedure that requires a lot of different exposures, do the one that has the highest exposure last, right? Do that one last. So we can also correct this if we do what's called an offset correction, but there's problems with the offset correction. So what an offset correction does is it normally takes an exposure with just nothing in the area of the image receptor. So we expose the image receptor to just the raw X-ray beam, right? And then it's going to offset, because it knows with a raw X-ray beam, it knows what it should get, right? Just big black field, right? And it's going to take, okay, what did I get? I know what I was supposed to get was big black field. What did I get, right? And if it sees some error of inconsistency in that big black field, it offsets for that. That's what that offset correction is. So it gets rid of that residual area. But here's a really interesting example of human error. Someone did the offset correction with the frickin' marker in the bucky, right? So it was expecting big black field, and what it got was big black field plus marker, right? Because someone's marker was wedged in the bucky. Now every picture that goes after that is going to have a black R tattooed into it. It's like you literally just branded the image receptor, right? Because it's always going to correct the image with a, oh, there was that area of low attenuation. There must be a bunch of dead pixels in the shape of an R, right, in that area. And so every image now that's ever taken with that system until that correction is fixed is going to have a big black R on it. Why is it black? Because the system is offsetting for the initial white R that it saw, right? That's why I'm saying it's like it's been branded there. So I thought this was a very interesting thing. And she says this signal is still very strong, and this image was taken 10 minutes after the initial exposure. That's how long this lasted because of this human error. All right, thank y'all so much.